Welcome, everybody. We'll start now. Welcome to this today's DAA seminar. It's a pleasure to have Dr. Melissa McClure as our speaker today. She's currently an assistant professor at the Leiden Observatory, Leiden University, Netherlands. Melissa did her undergrad at the University of Rochester and also worked for the Spitzer infrared spectrograph instrument team as a research assistant. So that's when I met Melissa for the first time when I was a postdoc there at Rochester. Melissa then moved to University of Michigan, where she worked with Nuria Calvet for a PhD on the influence of dust grain evolution on the structure of protoplanetary disks. She was then an ESO fellow at the European Southern Observatory, Garching, and then a Mary's Sklodowska-Curie fellow at the University of Amsterdam. So she joined Leiden Observatory in 2019 and has been there since then. Melissa's research interests have always been on protoplanetary disks. As you know, these are disks that are birthplaces of the planetary systems. So she studies the physics and chemistry of planet formation in these disks, both observationally and theoretically. She's the principal investigator of the JWST early science release program called the Ice Age. Today, she will tell us how to measure the unseen building blocks of planets in protoplanetary disks. A quick remark about questions. We will take questions in the end, so you can type in your questions in the chat window or raise your virtual hand. In case there are some urgent or questions that require immediate clarification, you can raise your hand and I will call you out for asking the question or direct the question to Melissa. All right, Melissa, the floor is yours.
Right. Hello, everyone. First, I'd like to thank Manoj and the Tata Institute for inviting me here to share my research with you. Just before we begin, the overall sketch of how the talk's going to go is I'll give you some motivation for why we have trouble measuring the unseen building blocks of planets and how we're going to go about sketching out a technique to do that. Then there'll be two parts to the talk, one focusing on more near-infrared observations of protoplanetary disks, and then the second part talking about the Ice Age JWST ERS program, which is open to the community, so it's something that you may want to get connected with at some point. So let's go from there. So first, to motivate this, I'm going to be talking about building blocks for planets. So what I mean by that are the basic elements and molecules that make up the planet. So there are, in particular, four elements that we know are cosmochemically abundant. So that's hydrogen, oxygen, carbon, and nitrogen. They are part of the top 6 elements by number density in the sun. And they also make up a large fraction of the human body. The fractions are given here for the sketch of the human body. So we know that they're really important to cosmochemistry, astrochemistry, and also biochemistry. However, these 4 elements are heavily, except for oxygen, are heavily depleted in Earth's core and mantle and crust. So the rocky elements, including iron and oxygen as well, make up over 99% of the mass of the Earth, and the volatile elements that are needed for human life only make up less than 1%. So we want to understand, going forward, first, how we got these elements on Earth, and what's the likelihood that we have a large amount of these elements in any given exoplanet that's forming in a protoplanetary disk. So Earth formed as a result of the star formation process in a protoplanetary disk that formed around the newborn sun. And the star formation process starts, so that this is the solar system here with Earth. The star formation process starts back in a dense molecular cloud when a particularly overdense core starts to collapse. That core will collapse to form a central star with a small protoplanetary disk around it and a protostellar envelope that's funneling material from that molecular cloud core onto the disk. Once it hits the disk, it's transported radially in towards the central star by spiraling in through the disk. Then eventually the envelope that funnels the material from the cloud onto the disk dissipates, and you're just left with the protoplanetary disk, which continues to act like a conveyor belt, moving material from the outer cold parts of the disk to the hot inner parts of the disk. And it's at this stage that traditionally planets are thought to form within the disk. Eventually, that disk either dissipates or accretes onto the central star or is blown away, and you're left with a solar system or an analogous thing to the solar system with planets in it. Now, if we take a different view of that, where here it's taking that diagram and saying this is the molecular cloud, and then you're collapsing a dust particle in through the protostellar envelope and onto the protoplanetary disk. The different ices that you acquire as a dust grain when you're in the molecular cloud will set the chemical structure for the disk. So if we take a quick look at sort of a standard model of a dust grain, you have a silicate core, which is something that probably formed in the outflows from AGB stars. It has an amorphous carbon component, potentially as like a sort of onion shell or mantle around it. And then within the molecular cloud, you had different layers of different types of ices that formed on the grain itself. So you would expect that first you might have a layer of water ice, which could have formed at higher temperatures, so not as deep into the cloud. And then you have last a layer of CO ice, which would have formed in the really cold, deep regions inside the cloud. And once you have this grain and it's formed and it's falling in through the envelope onto the disk, you start to hit different locations in the disk where the temperature is high enough as you're moving in toward the central star that different ice species can sublimate. So in this example, you've taken this CO-rich ice grain, or this CO-mantled ice grain, and gone past the location where CO would sublimate. And so you've released that CO gas into the gas phase, and you're left with this now water-mantled ice grain. And you just keep going in toward the star. You lose an ice layer each time you cross one of these so-called snow lines. So now we've lost all of the water. It's in the gas phase, and we have a dry carbon and silicate grain. We keep going further in. We lose the carbon. And further in, beyond that, we lose all of the silicate. And it's at this inner silicate rim where all of the dust, all of the solids that we had in the disk are now back into the gas phase. And the effect that this has on the composition of the solids in the dust, or in the disk, and the gas in the disk, it can be seen in this sketch from Oberg et al. 2012, where you can see that as you remove material from the solids, it goes back into the gas phase. And so you get this sort of step function for the composition of the gas and the dust in the disk as you move further in. And this has an impact on the composition of the planets that can form at different locations in the disk. We can actually see this effect in real life, not just theoretically, with the ALMA submillimeter arrays. So this is an example from a recent series of papers by Coco Zhang in 2019, 2020, where you can see with ALMA, they've observed the amount of carbon monoxide relative to what their modeled value for the molecular hydrogen is in the disk. And it's depleted in the outer part of the disk here. And then once you've crossed the CO snow line, the amount of carbon dioxide goes back up as that ice is sublimated into the gas phase. So we can actually see this happen in real life, and this sets the chemical structure for the disk. Now, this is important because planets can form at different points in the disk. And what we'd like to know when planets form is what the composition of that material is at their formation location. One of the primary places where we expect planets to form are so-called pebble traps. And these can be, for example, at the snow lines themselves. You can have a pebble trap that forms there, or you could have a pebble trap that forms at this inner edge of a dust ring. So essentially what happens is you have a negative pressure gradient moving from the outer part of the disk toward the star. And if you have something like a gap or a sublimation point, then you get a a peak in the pressure gradient followed by a dip, and then this causes a pressure moving in from the inner part of the disk to the outer part of the disk, and from the outer part to the inner part. So you build up with a set of millimeter to centimeter size pebbles that can collect right here. And these pebbles can't go any further in toward the star. And so this location where we think that you could easily form a planetary core by a process called pebble accretion or streaming instability. So one key question here is, in these systems where we know we have rings, so we should be collecting dust in these rings, what fraction of the carbon, hydrogen, and oxygen and nitrogen budget is available to form planets at this location? Normally, if we wanted to know the composition of solids in any type of astronomical object, we would look at the mid-infrared. This is an example of a protostar spectrum where you can see a large number of deep dips and different spectral features that correspond to ices and also silicates, so rocky material. And you get these dips and features because they come from different motions that the atoms in a molecule make relative to each other. So this is an example for water where you have different stretching and bending modes and wiggle modes, stop there, that produce some of these features. Now, the problem with looking at protoplanetary disks is that at the mid-infrared wavelengths, the midplane, which is where we're interested in measuring the composition of the solids, is actually optically thick. So essentially, it's like we have a black box. We can measure what's going on in the upper layers of the disk, but we can't actually access the midplane. So the thrust of my research in the past 2 or 3 years and going forward from here has been coming up with ways that we can indirectly measure the composition of the solids in this midplane. And what I'm going to show you today is that we can actually audit the disk material budget. So by knowing how much material you have moving in and how much material you have moving out, we can use that to infer the presence of pebble traps and then measure their composition. So we say we have input material going into the disk, the trap forms, and that has an impact on the amount of material that you get out at the end that sublimates in that final snow line and is released onto the central star to be accreted. The difference between these two values, the input and the output, represents the material left behind in the disk in these pebble traps. It's a bit like a CSI forensic exploration, where you know what started off the night before, you know what the outcome was of the crime, but in order to identify the crime, you need to examine this crime scene here and see what happened. And I think in this case, somebody replaced the caffeinated coffee with decaf coffee, and someone else was not happy. Another way to think about these traps is you can imagine that you're making a pot full of pasta or a pot full of rice. And when you dump the water plus the cooked rice or pasta into a colander, you get starch in the water that comes out of it. So this is sort of like you're saying you're measuring the starch in the water coming out of this to infer how much pasta or rice you cooked. And maybe there's some planetary meatballs mixed in with it, which would be exciting. So basically, that was the broad introduction for the talk. What I'd like to go through next in part one is how we measure that output gas abundance and how we can use that to infer the composition of the dust that's been trapped. This is work that I've done both by myself in 2019, but also with Karsten Dominik and Mikael Kama, my collaborators, in a paper that we just put out like last week. And then for the second part of the talk, I'd like to talk about how we can improve our measurements of the input composition in the outer part of the disk, the amount of ices that are moving into it. And this is what I'm doing with the JWST Early Release Science Program, Ice Age, with my co-PIs, Harold Linnertz and Edwin Bogart. And we have, for this project, there's a team of more than 50 international team members, and we're always interested in more people joining if it's something that you'd like to do. So first, let's talk about part one. So to remind you again, part one is where we're measuring these output elemental abundances. So I'm going to zoom into this region highlighted in magenta there, the inner part of the disk. So this is a representation of what that should look like. basically, at the end, as we saw before, you have silicate-rich dust that has lost all of the ices, that's moving in toward the central star. You also have the gas that's moving in toward the central star, which includes the sublimated ice leftovers. It hits this silicate inner rim. All of the silicates sublimate into the gas phase, and you're left with this pure gas accretion disk. This is where we want to measure the output abundances. From here, the material moves on to magnetic field lines that connect the star to the disk, and it's accreted along those until it impacts on the stellar surface, where it adds to the total mass of the star. So this is just a basic outline of the structures that you would expect to see within the inner 0.1 AU of a low mass star, like a T-Tauri star. So what I did in the 2019 paper was to take a set of 26 disks in the torus molecular cloud, and I obtained 0.8 to 2.5 micron size, or micron wavelength spectra of these disks using NASA's IRTF SPECS instrument. And just to show you how this physical setup translates to the actual data, this is a spectral energy distribution, so a plot of the brightness versus the wavelength of the inner part of this disk. So here you have the photosphere, so the stellar surface. That's this solid line, and that's we can remove that to get the excess emission that we see coming from these other structures. The actual data is here in the light gray curve. So the inner dust rim right here shows up in this near infrared and mid infrared emission excess. Then the magnetospheric accretion columns show up in the ultraviolet and the optical, and contribute a little bit to the lines that you see in the optical and near infrared. And finally, this inner gas disk shows up mostly through some very faint emission lines in the near infrared. And this was the new thing that we had figured out, or that I had figured out for this paper. Here is an example of one of these disks where I've removed all of the continuum emission contributions from the accretion shock and the inner disk. We're just left with the emission lines, mostly from the inner gas disks and somewhat from the accretion columns. So you can see that there are hydrogen recombination series, some of which again come from the accretion columns, but you can fit out the component that comes from that. We also have calcium, oxygen, neutral carbon, and neutral sulfur, as well as helium. And you can see in particular these very weak neutral carbon lines, which I boxed in red. They look very faint here, but the signal to noise on them is actually quite good, like a signal noise of 10 to 20. These lines have actually already been studied in the context of planetary nebula by Ashok and Banerjee in 2003. And it's a great example for the students of why it's important to read the literature, not just for your own field, but for other fields, because at some point I was searching for where these lines could come from and found these references to planetary nebula and went back, and it was fabulous. They identified all the lines, and I could just say, check, 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 check. We're definitely seeing carbon. So what I did in this paper was to take these carbon lines first and fit the electron density, electron temperature, and the carbon to hydrogen abundance ratio. And for this, we got for a set of 5 of those disks where you could actually get really good signal to noise on the line profile in order to do this fitting. And we found that overall, all of them appeared to have a depletion of carbon relative to what you would expect if you assumed solar abundances as the input. The depletion factors were really only significant at a 3 sigma level if they were greater than 12. So that meant that we identified 3 disks in which we definitely had depletion, which suggested that traps must have formed somewhere in the disk. Now, we couldn't tell whether the traps formed beyond the CO ice snow line, the methane ice snow line, or the carbon dioxide ice snow line. So it really could be anywhere in the outer part of the disk. And we can't say from the data that we have here where these traps necessarily formed. So that was the next big question. Can we use these data to identify where the traps the pebble traps formed in the disk. And the answer is, if you add additional elements to your analysis, then you can do that. So,
Melissa, could you take a question now?
yes.
Mine, go ahead and ask the question. Unmute yourself. Go ahead and ask the question.
Melissa, hi. Quick
Hi.
question. So how sensitive are your values, these depletion values, to the, let's say, the abundance of, like you're taking solar abundance, right? So if if it's not solar abundance, let's say it's less metal, it's metal poorer or metal rich, how would those results, how would this differ in that case?
Yeah, so these are written in terms of the solar value. I get out an actual C over H ratio, and then if you had, so if you were depleted in metals already, then you wouldn't detect a depletion in the disk. So it's heavily dependent on what you assume for your input values. That's exactly right, and that's why for the second part of the talk we really need to have better estimates of how much of each of these elements enters the disk. So that's an excellent question.
Thank you.
Okay. Yep. And now the transistors have to go again. Okay. There. So we expanded this analysis in a paper that just came out recently to the 8 million-year-old disk TW Hydra. This is a disk that's very close to us, so you get excellent signal to noise when you observe it spectroscopically. It also has very well characterized gaps in the disk using the ALMA millimeter array. So you can see here there's a central gap right here, which is quite deep, and then less deep rings in the outer part of the disk at around 20 AU, close to 40 AU, and then around 45 AU or so. So in this disk, the signal to noise was good enough that, and we actually had multiple epochs of spectra, so we were actually able to subtract off two different epochs from a low accretion epoch and a high accretion epoch, where we could then use those to isolate the hydrogen emission coming from the inner disk. So now we had a hydrogen observation that we could compare with everything else. We also had carbon, oxygen, nitrogen, sulfur, all of these other elements. So we essentially repeated this process, but with a larger set of elements, and found this for the result. So to explain this diagram, this is the abundance of each element relative to hydrogen in solar units. So it's essentially measuring the depletion factor, where the lower you go on the diagram, the more depleted you are. The elements are on the x-axis. You can see that we had 4 different detections with error bars, and then the rest are upper limits. If you look carefully, you can see on the top, I have a plot of the abundance relative to hydrogen for the different elements in meteorites, which should represent asteroids. So the gas pattern that we observe in TW Hydra is close to being a mirror image of what you would see in the meteorites, suggesting that whatever material we don't see in the gas phase of TW Hydra could be locked in something like a meteorite in the disk. The other patterns to note are that the elements that appear mostly in ices, so carbon, nitrogen, oxygen, and sulfur, are depleted by about a factor of 100 relative to the solar value, which again, we've assumed here that it was a solar input value, which could be different. The other thing to note was that the rocky elements are depleted by at least a factor of 10,000. And this difference between them seems to suggest that we can explain the icy element depletion by two pebble traps that formed beyond the water and CO snow lines. And this difference here with the rocky elements suggests that there's a third rocky or refractory rich trap right here at about 0.3 AU. So we can identify now the locations of the places where this material is being retained in the protoplanetary disk, where future planets could form. This is a bit complicated, but we ran a simple toy model that modeled how the dust was transported through the disk and where it starts to be locked out or trapped out of the transport stream. And we found that 96% of the dust mass flux moving through the disk is stopped by the time you reach this trap here at about 20 AU. So there are actually 3 submillimeter rings exterior to that. So the cumulative effect of those 3 rings is to trap 96% of the carbon-rich dust. And we confirmed this number by comparing it with the nitrogen depletion in the outer disk that had been measured by Van de Hoff et al. 2017, where they also found a 96% depletion. Then you trap about 3% of the dust at this inner trap at 2 AU. And that means that you end up, but by the time you've gone through this third trap that removes the refractory material or the rocky material, less than 0.02% of the original dust makes it back onto the star in terms of the silicates. And only about 1% of the icy material from the outer disk makes it back through in the gas phase. So what this means is that in that 0.3 AU pebble trap, we should be forming, if planetesimals form there, then they should be forming from material that's been heavily depleted of carbon, or conversely, you can see it as being enriched in silicon relative to carbon. So it could be forming something like an Earth-like planetesimal. In contrast, in the outer part of the disk, where we have this...
Melissa, when you say carbon-rich dust, do you mean pHs?
So when I say, yeah, so you split your carbon between the ices and potentially refractory carbon. It's not clear whether that refractory carbon would be in, like, probably not graphite, maybe amorphous carbon. You could have PAHs as well. Then there's this whole question of how you would, if it's PAHs, they're much easier to burn off than if they were, say, amorphous carbon. So that I'm implying here that the inner disk is probably poor also in the refractory carbon, but that ties in with this question of how you whether you can destroy refractory carbon. There's a recent paper by Ted Bergen on this. So it's not a definitive answer to your question, okay, but it's
go ahead. Yeah, thanks.
Yeah. So in the outer part of the disk, we had a lot of both nitrogen-rich ices and carbon ices, and this could produce something similar to Pluto, but maybe actually even more nitrogen-rich based on some modeling that we did in this paper. So we need to confirm this finding of the very nitrogen-rich nature of this ice in other sources before we can say anything for sure. But we're definitely starting to see regions of these disks where the solid composition resembles solar system bodies that we know formed at certain locations in the disk. In the future, we're following this up by applying the technique to other disks where we also know that there are gaps that we could actually test whether ices and dust are being held back in these rings. For example, this is a subset of the collection of disks with gaps shown by the D-Sharp team. And we have some of these objects in a sample of disks that's being analyzed by my PhD student, Arjun Sturm, to look for signs of radial drift at younger times. Radial drift is the motion of the dust grains in advance of the gas going through the disk. We're also, I'm planning to follow this up with a study looking at these lines in younger disks to see how early you start to form these traps. So that's one way of going forward with this in the future. Another way of going forward is that we could refine what our assumed input abundances are. And this is exactly Mayang's point that he just asked with the question about whether assuming solar abundances is really the right decision. It's the easiest thing to do because we have complete abundances for a number of different elements if we assume solar abundances. But at the same time, you can imagine different scenarios where depending on whether you're forming in a different part of the galaxy, you may either be metal rich or metal poor. And that could also depend on what time you form. So what we'd like to do is to actually measure the input abundances into the disk in particular regions and see how they compare with solar. So that's concluding the first part of the talk. Measuring the input abundances is going to be the second part of the talk, looking at JWST. So if there aren't any questions right now, then I'll skip into that. Okay. So if we go back to this picture that we have of auditing the composition of the disk, where you measure the input abundances and the output elemental abundances, we've completed this part for developing a technique for how to do that. So now we want to measure the input abundances. And we have, again, this picture where we said that for a particular dust grain, you started out with your silicate core, and then in the molecular cloud stage, you actually formed a number of ices on the grain. And then the grains fall through the cloud core, the protostellar envelope, and onto the disk. So what we'd like to know is how much ice actually forms here and whether it's comparable to a solar abundance worth of that particular element. So you can measure the ices, as we saw earlier, through mid-infrared spectroscopy. You need to use specific targets and specific lines of sight because you basically have to have a hot continuum source behind your ices in order to see them in absorption in the mid-infrared. So in a molecular cloud, you can look at a background star and you'll see the hot continuum from the background star with the cold ices in the cloud imprinted on that spectrum. In the protostellar envelope, if you look toward the central star, you'll see a hot outflow cavity, which has a continuum, and you'll see the cold ices in front of that. And the same thing for the disk, where you look now at very edge-on disks, and you're looking at the cold ices seen against the continuum of the inner part of the disk. And this is what the best state that we have right now of spectra look like for each of these categories using the Spitzer IRS instrument and some ground-based observations and then ISO here. So what we can do with mid-infrared ice spectroscopy, we can observe carbon-rich ices. So here we have CO2, CO, and methane. We can also observe all of the oxygen-rich ices, so water in addition to these other ones that have oxygen, and nitrogen-rich ices. So we can basically cover all of the major elements that we were interested in before. You can also look at sulfur-rich ices, which I haven't shown here because those are a bit harder. But you can basically get the complete set of elements that you're interested in. At the same time, you can get spectroscopy of the silicate feature, which can tell you how much magnesium, silicon, and iron you have. What you can do in addition to that, with better mid-infrared spectroscopy than what we could get with Spitzer, is you could look for complex organic molecules. And these are molecules that have more than 6 atoms. They're all carbon-based. They show up in particular for laboratory ice spectra in this region between about 7 and 8.5 microns. There are hints of these ices in ISO spectra. So ISO was the one generation before Spitzer Space Telescope. So you can see these little dips here, which correspond to, these 3 correspond to complex organic molecule features. These are laboratory spectra, so you can see acetaldehyde and ethanol line up roughly with these features. Now, these ices, the simple ices, we know we see them in comets, and they're probably what brought the small amount of these elements that we have to Earth, possibly also in asteroids. And comets may also have brought these complex organic molecules, including potentially a biomolecule, to Earth. And this could have actually kickstarted Earth's biochemistry to give it an edge in how fast it starts producing life. And that's because if we look again at our diagram of how much of each of these elements is in the human body, these elements in their bulk form first form complex organic molecules, which then eventually form macrobiomolecules and water, which are what we need to have life. So it would be very exciting to see these molecules in ices because they can already form in molecular clouds, and we could trace them all through the star formation process to see whether comets came prepackaged with these potential building blocks of life. So why couldn't we do this before with Spitzer? Well, or how much have we done before with Spitzer? So simple ices have been measured for a number of protostars with Spitzer. There were a lot of these measurements. Here you can see a protostellar spectrum in red and magenta. And we have a few spectra of ices, really good quality spectra of ices behind through molecular clouds on lines of sight toward background stars, and that's in black here. However, those were isolated individual observations, and a lot of them didn't have really good signal to noise. And if we look at disks, seen edge on, this is the best ice detections in a disk that were done with Spitzer, where the disk did not have an envelope around it. And you can kind of see that you've got features that sort of line up with these ice features, but the disks are about 2 decks fainter than the protostars in the same star forming region, because you're really like seeing them edge on, so you're blocking out most of that hot continuum. And that means that in order to get good ice measurements for these disks, we actually need a much more powerful facility than we had with Spitzer. So this is where we introduced the James Webb Space Telescope. It is a joint ESA-NASA Canadian Space Agency space telescope. It should launch, knock on wood, in October 2021. It'll have a 5 to 10 year lifetime. And in the first 1 year long cycle, there will be guaranteed time observations that the instrument builders get, early release science program observations, and general observer programs. The observation call for general observer programs is November 24th of this year. So if you get inspired by this talk, you should go out and put in a proposal. I'm going to talk for the rest of the talk about the early release science program. So these needed to be programs that were that constructed representative data sets for a particular science case. They needed to be executable in the first 5 months of observations. They needed to have plugs into multiple science cases that could get the community excited. They're non-proprietary, which means that basically as soon as I get the data, you guys get the data, if you want to access it. And we had to say that we would deliver science-enabling products that would help the community of users create proposals for the Cycle 2 call for proposals. So there were only 13 of about 106 proposals accepted. And Ice Age is the only proposal that is explicitly related to star formation. We have a really big team of 50 plus members representing a number of different countries. We always welcome new science collaborators who are interested in joining the team. We're a mix of observers, about 50%, and then the rest split between laboratory ice observations and chemical modeling, because we need all 3 components to work together in order to analyze the data. So what will we get with the JWST Ice Age program? This is an example of that ice spectrum that I showed you, but as it would be seen from the ground. So the black rectangles indicate where the atmospheric transmission goes to 0, where the atmosphere blocks out the observations. So you can see that if we were to observe it from the ground, we wouldn't really get that much. So with JWST, we'll get the full range from 2 to 28 microns. So all of these basic ice features plus the comms. JWST has multi-object capabilities, so you'll actually be able to just put an array on a particular molecular cloud, open up slits over each of the background stars that you anticipate seeing, and get individual spectra for these background stars. So we'll be able to map the ices. We can also have a factor of 25 times more spectral resolution at this critical wavelength range around 8 microns, where we expect the complex organic molecules to be. So we'll be able to actually identify individual comms, hopefully. And the JWST is also 50 times more sensitive than Spitzer was in this region. So we should be able to answer the questions: how much simple ice exists in prestellar cores and disks, which is still remaining from what we knew from Spitzer, which was mostly protostars. And we'll be able to tell how complex these ices should get by the time they're incorporated into comets within protoplanetary disks. The specific targets that we're going to look at with the Ice Age ERS program are all sort of focused around this dense dust ridge, which can be seen here at 0.85 millimeters in the Chameleon-1 molecular cloud. So in this dust ridge, we have a dense pre-stellar core. So this is one of these cores that hasn't yet formed a star at the center, but it's gravitationally unstable and will collapse to form a star someday. We have a class 0 protostar, so the youngest type of protostar that you have that basically is just the star and a tiny, tiny disk and mostly envelope material. And we'll be able to map those using the NIRCam wide field spectrograph mode. We also see in cyan here a bunch of different background stars that we can map as we move from the diffuse material onto the dense ridge. So with that, we should be able to see how much ice you gain as you go in, as your material gets denser and denser and denser. We'll also get IFU observations with NIRSpec and MIRI of this older protostar right here, which we have a scattered light image there. And also similar observations for an edge-on disk, which is indicated here. So we'll basically get every single stage in the star formation process from the cloud all the way through to the disk, all within the same narrow region. So we can really see how the ices chemically evolve from where they're in the cloud to where they go into the disk. So we'll really be able to pin down our input abundances into the disk using this program. From the perspective of what we'll give back to the community, there will be these science enhancing products. They'll include observations, so all of the different stages of star formation. We'll produce an enhanced data reductions for all of our sources. We're working to make the pipeline a little bit better for the observations with the NIRCam wide field spectrograph mode. And we'll have a best practices document for people who want to take what we learned from the ERS program and apply it to their cycle 2 observations. We'll also provide a model grid that's tuned to the specific physical conditions of the Chameleon-1 star forming region. And we'll include the newest laboratory absorbances and opacities in this. So people can take this and apply it to other star forming regions galactically. The grid will also include an expanded module to allow people to make predictions about ice content in other regions of the galaxy, but also in extragalactic environments like the LMC and SMC and external galaxies. Again, in preparation for the Cycle 2 call for proposals. And there will be a update to the Laboratory for Astrophysics at Leiden, their ICE database, where it will have spectroscopy of all of the simple ices for a range of temperatures and mixing ratios, and opacities that can be used, opacities for these ices that can be used for different grain sizes and put into radio transfer codes for a number of different applications. We'll also have rates for comms under different conditions and spectroscopy that you can use to identify comms in your own spectra when you get them back from JWST. So that's completing the second portion of the talk. Just to briefly summarize before taking questions, from the first part of the talk, what I was hoping to convey is that you can use the atomic composition of the gas that's being accreted onto the central star to probe whether you have formed pebble traps in the disk during the time period that it took for that parcel of gas to move in from the outer part of the disk. You can also combine this abundance measurement in the inner part of the disk with abundance measurements from ALMA to determine what the efficiency of trapping is at different locations in your disk, and measure the grain composition at those locations as well. Then for the second part of the talk, the program with JWST should provide for the first time a estimate for what the input in ice abundances into the disk really is, whether it's solar or whether it's metal poor or metal enriched is something that we really want to know. And these will be measurements of the ices in the disk right before they are incorporated into comets in the comet forming region of the disk. And last but not least, Ice Age will provide the star formation community with both a free set of data and also a free set of tools that you can use to start using JWST for your own programs in the future. So with that, I'd like to say thank you very much for your attention, and please let me know if you have any questions.
Thank you, Melissa. Thanks for that wonderful talk. Yeah, let me applaud on behalf of everyone. So we can have questions now. So please raise your hands, then I can call you out and you can ask the questions directly. Yeah, Mayank, go ahead.
Yeah, Melissa. When you were showing the dust traps, you said that by knowing the composition of the atomic gas which is falling, we can also sort of locate the position of the dust trap. So has there been any attempts to actually image the dust traps with, let's say, ALMA or something, whether there's an overdensity at, let's say, you showed at 0.3 AU, your model predicts a dust trap. So whether it's possible to actually follow them up with ALMA and see whether, do we find overdensities at this region or something?
Yeah, so in principle, that would definitely be possible for the case where we do this analysis on a disk that has no ALMA data. Then we could say, oh, there's a dust trap. Let's go look at it with ALMA. For the case that I showed, ALMA had already looked at it, so we knew that there should be a dust trap there based on the fact that there's the disk gap. I think actually measuring an overdensity in the dust, that's been done with ALMA for IRS 48 by van der Morel 2013. I think they had a clear asymmetric overdensity. So it's one of these, like, it looks like a banana with like, instead of a ring, there's like clearly a concentration of dust on one side of the ring. But I think a lot of these pebbles, once they reach millimeter or centimeter sizes, they actually drop out of what ALMA can see. So if we got to a point where you really were just about to form planets and you had these really big pebbles, it might not be distinguishable with ALMA from what you would see for a less evolved system. So you might have to go to something like the next generation VLA or something like that.
Manoj, I have a question. I cannot raise my hand.
Yeah, go ahead, Basudhi.
Yeah, okay. First of all, thank you, Melissa. Very nice talk. My question is more a more general one. Could you just tell us a bit about the laboratory activities? Like, what is the status? Because you mentioned that there'll be new measurements of ices, and so, like, just to tell us, like, how far do we know from the labs? Like, do we have features in the ices which have been observed and lab has not been able to reproduce them, or is it that with the improved sensitivity of JWST you expect to see more features, and that's what you're trying to match?
So more of the second case. So the problem with Spitzer and ISO was that once you get to about 1 to 3% of the continuum, which is the sort of the level that you would expect for the calm ice features in terms of how deep they are relative to the continuum, then you start running into the instrumental effects with the spectrographs that were on the space observatories. So from the laboratory experiments, I think I have a backup slide on this. Sorry, I just had to switch through all the backup slides. Okay, so this is an example where these are basically 4 different complex organic molecules. So there's methanol, which should be the dominant COM by mass, and then dimethyl ether ethanol and acetaldehyde. And you can see that they share a lot of features because they have similar functional groups. So if you want to identify them, you actually have to use, instead of some of these stronger features here, you have to use some of the weaker features in this 6 to 10 micron region. So right now in the laboratory at Leiden, we have a list of complex organic molecules that we anticipate being in the ices based on the fact that they've been detected in the gas phase with ALMA for different protostars. And they're just running down the list and producing these sort of spectra for those COMs. So for each one of these spectra in this image, there's like a complete grid of temperatures spaced by about 10 to 20 Kelvin each, going from 10 Kelvin up to like 140 Kelvin, so that you can see how the features change with like if they get crystalline or things like that. There are some other lab groups that are also doing, so these COMs are typically, in the Leiden group, are typically done under, are typically measured under conditions that would simulate the cold molecular cloud cores. There are other groups that are actually saying, okay, well, you could create more radicals in the ices as you're infalling through the envelope and you're exposed to X-ray and cosmic rays and UV radiation from the central star. So they're actually doing bombardment experiments on some of the comms. So what we're hoping to do, we have about 7 different lab groups. So we're trying to create a they all have their own databases. So we're trying to create sort of a meta database that links to each individual team's database so that people who want to search for the absorbance spectra for these molecules can just go there and sort of have a buffet that they can choose from, organized by the particular chemical formula for the molecule.
Thanks.
Okay.
We have another question from Jessie Jose. Jessie, please go ahead and ask your question.
Yeah, hi, great talk. So I just have a question related to what Mayank asked about the abundance. So all these Spitzer-based analysis on disk have been on solar abundance objects. But if you go to a low metallicity star-forming environment, so what is the disk composition? What do you expect? Is it 1-to-1 correlation? So my question is, assume a star-forming region in the very low metallicity environment, and the stars with the disk around them, the protostars with the disk around them. So the composition of the disk, are they 1-to-1 correlated with the medium, or do you expect some variation in them? So
I would expect variation. I think this is something that we haven't really gotten into with the experiments that we're doing yet, because we're just starting and it's easier to assume a solar metallicity. But I think in those cases, if you were studying the disks in those regions, you might consider getting the stellar abundances for a large number of sources in that region and sort of taking an average to see sort of to infer from that what you think the input abundances were. I've seen a couple other people looking at this in reference to exoplanet studies. It might also apply to what we're doing.
okay, yeah, thank you.
There is a question in the chat box, Melissa, so I will read it out to you.
Okay.
This is from Gunesh Tangjam. He says, very nice talk and very informative, thanks. The question is, how far the observed spectra is compatible with the laboratory reference spectra in terms of the simulated physical conditions?
Yeah, so this is a good question, and it's something that is difficult to tell right now with the Spitzer IRS spectra, because they hadn't. So the spectra that I've shown observationally were mostly from either the ISO Space Observatory or Spitzer. And in those two cases, they're not spatially resolved. So if you really, so you're sort of taking the structure that has the central protostar, which has some hot regions around it, and then the colder regions in the cloud around that, and you're adding all of that up together. So I think there are we have laboratory experiments specifically for the cold regions, and then other ones specifically for the hot regions. And right now, with the Spitzer observations, we don't have either the spatial or actually spectral resolution to resolve the different effects that you would get for those two regions and separate them. That's definitely something that we'll be able to do with JWST. So the resolution that we should be getting there is around 2700 to 3400 resolving power, and Spitzer was in the same region was around 120.
Okay. Any more questions?
Yeah, so I have a related question actually. So since you mentioned that it might actually work if you have enough spectral resolution, though not spatial resolution, what about observing with, say, XS, which is on Sophia?
Mm-hmm. Yeah, so that should work, I think, for massive star forming regions. And I think people may have done that, but the problem there is that so I've tried looking up some of our, integration times for some of our targets with XEs, and they're just too faint. So okay. So if you had like a massive star forming region, you could I think with models disentangle some of these, the hot versus the cold regions, if you had XE spectra and the right set of laboratory observations. But
Yeah,
that's
but
sort of
that
like
will probably work only for the Orion. Anything else is too far away.
Yeah.
Thanks.
More questions? Please raise your hand or just unmute and ask yourself directly. Yeah, while people ask questions, I have a question, Melissa. So you talked about this carbon dust and the depletion. So, but then in protoplanetary dust and in the interstellar medium, carbonaceous dust is not the dominant component of it. It's a silicate dust, right? So your analysis is probably not sensitive to. I mean, you're not saying anything about the silicate dust.
Correct. So so for the simple transport model, we were just using carbon because we could say, all right, we assume most of the carbon ice is in CO, and then we have carbon dust that is more refractory than CO, which could include CO2 ice, but also refractory carbon. And for the silicates, because you just have that one snow line, and you don't have, or you have the inner silicate rim. And you don't have, for most disks, any kind of observation of silicon in the gas phase in the outer disk. It becomes really model dependent.
Yeah, so my question really is, so what you're tracing is the kind of a minor component of the dust, whereas most of the dust really is in silicate, the refractory dust.
Well, so keep in mind that when we say like we're locking out like 96% of the mass of carbon-rich dust, that's going to have like a silicate core with it. So we're not directly measuring what's happening to the silicates except at that inner silicate sublimation rim. But we're assuming that every time you're locking out carbon dust, you're also locking out silicate dust. And we're doing everything.
So you call this entire structure as a dust grain with the silicate core and this ice mantles around it. So the whole thing.
Right.
Which automatically includes silicate. Okay. Right. All right. More questions, comments? I'll give it 30 seconds for people to sort of, raise their hands. And if you don't see any more questions, then we can sort of conclude.
I have a question.
Yeah, go ahead.
So, so how would this, the abundance of the disk reflect in perhaps the abundance of the protoplanet or eventually the exoplanet? Do you have any? Can you say something about that?
Yeah. So that's a great question. So that it's a complicated question because essentially what I'm saying with this study is we're measuring the place where you would start to form a planetary core in these dust traps. So that will set the bulk abundance of the solid part of the planet. But then if you have migration, then it starts to get more complicated, because then if the whole disk either expands a little bit or contracts depending on what the temperature structure looks like, or if the planetary core itself starts to migrate out of its formation location further out in the disk or in, then you're going to end up with a different feeding zone. So you could get sort of a composite composition for different locations in the disk. And then once you start adding onto that gas accretion, you could accrete the gas at a different location from where you accreted the core. So there's actually a number of research groups like Niku Med-Hudson at Cambridge, I believe, or maybe Oxford, where
Cambridge IOP,
yeah.
IOP.
So they're looking into how you would take, like, suppose you measure an exoplanet atmosphere and you get water and CO, and you can construct a C/O ratio for the atmosphere. Ideally, you would say, okay, well, for disks, I know we have this 2D map of what the composition looks like in the disk. So let's say we compare that C/O ratio from the exoplanet with the C/O ratio radially in the disk, and we say, okay, well, the planet must have formed here. But if you have migration, then everything gets complicated. So then you actually need like a model of how your planet may have moved through the disk. And so his group, I think, is working with some planet formation modelers to come up with it's like a population synthesis thing for exoplanets. So you say, if you start planets at different locations in the disk and then you migrate them at different times, what's sort of the distribution for the atmospheric composition values that you would get, to see if there's any way to tie like the carbon over oxygen ratio versus the nitrogen over oxygen ratio to where you formed different parts of your planet. So it's a great question. It's like a completely open area of the field.
Okay, so there is another question. I can see a raised hand. So please go ahead and ask. I can't read your name. It's written in Bengali.
Yeah, very nice talk. So I had a slightly different question. Suppose whenever we discover a planet, for example, exoplanet, how do we estimate the surface temperature of the planet? Like you need to know the composition of the atmosphere, right? For that to estimate. How do generally astrophysicists or astronomers go about this?
So I'm going to give you my version of this, which is not the expert version because I don't model planet atmospheres, but you can. There are certain elements like sodium and I think molecules like titanium oxide that you can sometimes detect in the like transmission spectrum from some of these exoplanets, and that can give you a clue as to what is in the atmosphere. You can also measure water, carbon monoxide, and I think methane in a number of the atmospheres, and then you can use those to say you can use opacities for those materials to then combine with the distance from the planet to the central star and work out what the atmospheric temperature should be. And I know there are a couple of other additional things that you can do. I think with like the what's this? So the star will heat part of the planet's atmosphere, and depending on the circulation patterns, you might actually see a difference in the heating pattern for the planet as it's rotating and like a hot stream is going out through the equator. But this is also not my specialty. So
okay. Yeah, but some gases, presence of some gases will definitely increase the temperature, right? For example, carbon monoxide or even carbon dioxide, for example, or the methanes and the greenhouses gases, for example. And
exactly.
Is the method same for doing the calculation, for example, for a planet of solar system, or there are other considerations as well? Does people even calculate that, or
you mean for atmospheres
for
in the solar system?
Yeah, no, outside solar system, for example. Is this technology sophisticated enough that people do those things? Or
so I think right now, in a pre-JWST era, we're still trying to get good measurements for the abundances of those of like water and CO and methane in the exoplanet atmospheres. I'm not sure if we've moved to the point where we could really say we are very sure that this particular exoplanet has, an abundance of whatever plus or minus some value. Like I think we're not quite there yet.
Understood. Okay. Thanks.
More questions? Questions, comments? All right. If there are no more questions, let's thank Melissa again. Thank you very much, Melissa, for that very informative and lucid talk. And thanks for your time.
Thank you guys very much for having me. This was a lot of fun.
All right. Thank you.
Bye, everyone.
Bye. Yeah, so there might be, so we should keep this conversation going, Melissa. Maybe, later we'll see.
Yeah. Well, so I would